Hello, my name is Jordan Street, and this is an overview of my course project for pattern recognition at the University of Florida in the ECE department. My project focuses on the face recognition problem and specifically the implementation of the Eigenface algorithm. So in this video, I'm going to go through the general face recognition problem, highlighting some existing approaches, and then talk about specifics of the Eigenface method and provide charts for the algorithm performance, and finally draw some conclusions based off of data gathered in the algorithm implementation. So the general problem, you're given an image and you need to do a few things. One, you need to determine if there is a face in that image. Two, if there is a face, you want to be able to ID the subject, and then also provide some sort of metric for your match accuracy. Generally, you're concerned with the accuracy of your algorithm along with the speed you can run it, so it's execution time, generally for application in real-time systems. So applications of face recognition, certainly defense is a major one, being able to remotely identify subjects from images, for example, UAVs, also large-scale data processing. You have a lot of different devices taking pictures, and you want to be able to scan them all quickly and identify somebody. In the civilian industry, certainly biometrics, your phone, be able to unlock it based off of a picture of your face. And then also local law enforcement, being able to integrate traffic cams, ATM cams, and quickly tie that in and be able to search for a particular person through all that data. So there's a few existing approaches. Probably the most popular one is the Viola-Jones object detection framework, which basically uses features to classify objects. There's different statistical methods, such as principal component analysis, which is what this method is, the Eigenface algorithm. And then also linear discriminant analysis, or Fisher faces, is an algorithm based off of that. There's model-based algorithms. For example, bottom right, you see a mesh wireframe giving a 3D model of a person's face. And then hybrid approaches, which combine multiple different techniques. So the Eigenface method is really just a specific application of principal component analysis. You have high dimensional data. For example, a 100 by 100 pixel image would give you 10,000 dimensions. And then you use principal component analysis to represent that 10,000 dimensional vector in a smaller subspace. For testing and training, we're using the AT&T Face database, which has 10 images of 40 different subjects with varying lighting conditions and facial expressions. So you start by taking all of the images, which are n by n matrices, and concatenating each of the columns to form one n squared by 1 vector. You then compute the mean face image, which is shown in the bottom right as the blurred face, and subtract the mean image from each of the training images. You then calculate the covariance matrix for those training images shown here and compute the eigenvectors of that matrix. We run into problems though, because if the images are 100 by 100 pixels, that's a 10,000 dimensional vector, and then we need to compute the eigenvectors and eigenvalues for a 10,000 by 10,000 matrix, which is very difficult to do. So a trick we can employ is to, instead of computing the eigenvectors for AA transpose, we compute them for A transpose A, which is m squared by m squared, again, where m is the length of your training data. So in this case, we have 280 training images. We're only computing the eigenvectors and eigenvalues for a 280 by 280 matrix, which is definitely feasible. So like I said before, we calculate the eigenvectors and eigenvalues of A transpose A, and then using some clever linear algebra techniques, we can back out the eigenvalues and eigenvectors for AA transpose. So then, depending on the number of principal components we want to preserve, which in this case k, we choose the k largest eigenvectors, which correspond to the k largest eigenvalues. And then we make sure that the eigenvectors are normalized to unit length of 1, so they're forming a basis for our face space. So we then project each of the training images onto the face space. Then if we're given an image we want to ID, we subtract off the mean face, and then project that image into our face space. We can use a simple metric such as Euclidean distance to find the subject which minimizes the distance to our projected input image, and if that distance, which is treated as an error, is within a certain threshold, then we say that we've identified the input image. Other implementations use a different metric such as Mahalanobis distance in their calculations. So we have different methods for evaluating the performance of our algorithm. The first one we're going to talk about is just referred to as accuracy, which is the number of successful identifications divided by the total number of images in the testing set. So we have 280 images. If the algorithm correctly identifies all 280 of them, then we say that it is 100% accurate. We're then going to present a few receiver operating characteristic curves, which are generally used for statistical tests, and then also present an example of a face reconstruction from the face space PCA basis. So this shows the accuracy of the algorithm as a function of the number of principal components used. So you can see if we take the entire 10,000 dimensional vector and compress it down to one dimension, we get about 20% accuracy. So it'll be right 1 out of every 5 times. And then you can see that as you add more principal components, the accuracy of the algorithm improves. Up until about 12 seems to be the magic number, where we don't really get any improved performance after that. So using 12 principal components, again, it's taking this 10,000 dimensional vector and compressing it down to 12 dimensions. We can ID each of the faces in our testing set about 95% of the time. So we then have a few different ROC curves with various numbers of principal components used. For this first one, we're only using one principal component, or we're compressing the 10,000 dimensional vector down to 1 dimension. And you can see the performance is not very good. Consistent with our previous graph, we're getting it right around 1/5 of the time. However, if we add just 2 more components, you can see the curve is shifted up into the upper left-hand quadrant, which is what we like to see. And then adding more components, again, shifts the curve farther, giving better performance. So this shows reconstruction of an image by adding in additional components from our original mean image. In the top left, we have the mean image for our entire training set. And then the bottom right, we have the image that is passed to the algorithm. So you can see as we add more components onto the image, we get a representation that is closer to the original image. It's interesting to note that, as we saw before, we really only need 5-10 components to be able to ID the subject 95% of the time generally. So you can see what it looks like with 11 components. It's not very clear to us, but the algorithm is able to get enough information and enough variance in just those 11 components to be able to successfully ID most of the test set images. So conclusions off of this are: we verified the application of principal component analysis to the face recognition problem, which is the Eigenface algorithm. We saw that it performs fairly well in its just plain state. There's other tricks you can apply to it, such as linear discriminant analysis to boost the performance. We saw efficient ways of calculating the eigenvectors and eigenvalues for the algorithm, and then saw comparable performance to other methods used currently. So there's a few different files I'd like to go through. The first one is this parse data file, which takes the images from the AT&T face set and parses them randomly into training and testing directories. We then have the create observation vector and create test vector files, which take the images from the testing and training data set and create matrices where each column represents the concatenated columns of an image. And those are used in evaluating the algorithm and the actual PCA part of the algorithm and other parts as well. We have the main PCA file, which runs principal component analysis. We can specify the total number of components we want to preserve. Then have a few files for PCA ACC or PCA accuracy. This is the core file which evaluates the accuracy for a certain number of components. And then this file will generate the plot we saw in the presentation earlier. We have also the functions for plotting ROC curves here. This one goes through a few different numbers of principal components, and this is the core function for creating the ROT curve. We also have this PCA demo file, which we saw when we created the reconstruction with varying numbers of principal components from the image projected onto the face space. So there's two functions that weren't shown in the presentation. The first one is this PCA comp demo, PCA comparison demo, and this will show similar to the face reconstruction function. It'll just do that for two images side by side. So for example, right here, this shows the reconstruction of two images from the same subject with varying amounts of principal components used. And it's neat to be able to see how the images resemble each other up until you reach a certain number of principal components, and you can start to see the variation developing. There's also a function which allows us to view all the images associated with a particular subject. So for example, subject 5, we can run this and it'll show us each of the training images and testing images used in the algorithm.